Okay, this is number 78 on chapter 10. A uniform solid sphere of radius r is placed on the inside surface of a hemispherical bowl with much larger radius, capital R. The sphere is released from rest at an angle theta to the vertical and rolls without slipping. Determine the angular speed of the sphere when it reaches the bottom of the bowl. Okay, so first, I'll redraw the diagram. And the ball is here, and that's like the center of the bowl or circle, and this angle here is theta, and the radius is big R. Okay, so first of all, when the ball is initially here, it has potential energy, gravity, and it has no other energy. When it's at the bottom of the bowl, we're going to call that the 0 point, and there is no potential energy of gravity, but there is kinetic energy gravitational because it's rolling, and kinetic energy translational because it's the whole ball is moving. So, for potential energy, we need to find the initial height of the ball. So let's say at first we'll call this our 0 point, but that will change later. So this, we want to find the height of the center of mass, which is going to be here. And this whole length is big R, and this small length is little r. So then this part is going to be big R minus little r, which means that this height is going to be r minus r cosine theta. But that isn't, oh, and then, wait, yeah. So then, if we want to find the initial height of the center of mass in relation to this point here, then we'll do this length, which is big R, minus r quantity cosine theta. So then we'll do r minus big R minus small r cosine theta, and we'll say that that's going to equal our height. But that is not actually our height, because when the ball is at the bottom of the bowl, its center of mass is not here, but it's actually here. So when we do big R minus that length, then we'll get the height relative to this point here, but we need it relative to this point here, and this length is small r, so we're going to subtract the length of this small r, because the height is going to be relatively shorter. So if we expand this, it'll be negative r plus big R minus r cosine theta plus small r cosine theta equals h. And if you simplify it, it'll be big R minus little r times 1 minus cosine theta. And that's going to equal our height. So here, they don't tell us the mass of the ball, but that doesn't matter for now because it'll eventually cancel. So potential energy of gravity is mgh, so mg times r minus r 1 minus cosine theta equals, so kinetic energy rotational is 1/2 the moment of inertia times the angular velocity squared plus translational kinetic energy, which is 1/2 mv squared. So if we multiply both sides by 2, we'll get 2 mg times big R minus small r 1 minus cosine theta equals the moment of inertia times angular velocity squared plus m, and then a velocity equals radius times angular velocity. So this will be mr squared, angular velocity squared. So if you move everything to one side and isolate angular velocity, then you'll get 2mg times big R minus little r, 1 minus cosine theta, over the moment of inertia of the solid sphere, plus mr squared, and the whole thing is square rooted. And from the chart in the book, the moment of inertia of a solid sphere is 2 over 5 mr squared, and then, so that's moment of inertia, and then plus mr squared. All that square rooted, and then you'll cancel out the m's, and then if you simplify that, you will get 10g r minus r, 1 minus cosine theta, over 7r squared, and all of that under a square root. And that is your answer.